A single object in the universe produces more energy in 1 second than our sun will generate across its entire 10 billion year lifetime. That's not science fiction. That's happening right now, somewhere in the cosmos. And it's just one contender for the most powerful thing that exists. The universe doesn't do subtle. When stars collapse, when galaxies collide, when space itself tears apart at the seams, the energy released makes our most powerful nuclear weapons look like birthday candles. We're talking about forces so extreme they bend reality, twist atoms into impossible shapes, and blast radiation across billions of light years. Here's what makes this question fascinating. Power comes in different forms. A magnetar has a magnetic field so intense it would kill you from 1,000 kilometers away by ripping apart the atoms in your body. A quasar shines with the light of 1 trillion stars from a region smaller than our solar system. A gamma-ray burst releases more energy in seconds than entire galaxies produce in years. So which one wins? The answer depends on how you measure. Raw energy output, sustained power over time, destructive potential, the ability to warp space itself. Each metric crowns a different champion, and understanding these cosmic titans reveals something profound about how the universe actually works. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. Let's start with the most obvious candidate, quasars. These objects confounded astronomers when they were first discovered 60 years ago. They looked like stars through telescopes, but the math didn't add up. They were impossibly bright and impossibly distant. What astronomers eventually realized changed everything. Quasars aren't stars at all. They're the beating hearts of young galaxies, powered by supermassive black holes consuming matter at a rate that defies comprehension. The fastest growing black hole we found, designated J0529-4351, has a mass of 17 billion suns. Every single day, it devours material equivalent to our entire sun. Think about that for a moment. An entire star's worth of matter, gone in 24 hours. And this isn't a quiet process. As that matter spirals toward the black hole, it forms an accretion disk where friction heats the material to millions of degrees. The energy released is staggering. J0529-4351 is over 500 trillion times more luminous than our sun. That number is almost meaningless because our brains can't process it. But here's a comparison that might help. This single object outshines the combined light of every star in the Milky Way by a factor of thousands. Its light has been traveling toward us for over 12 billion years, and it's still bright enough that we can study it in detail. Quasars emit their energy across the entire electromagnetic spectrum. X-rays, ultraviolet, visible light, infrared, radio waves, all of it pouring out from a region about the size of our solar system. Some quasars generate 10 to 100 times more energy than our entire galaxy, which contains somewhere between 200 and 400 billion stars. The physics behind this power is actually elegant. Black holes are the most efficient engines in the universe for converting mass into energy. Nuclear fusion, the process that powers stars, converts about 0.7% of mass into energy. That's what makes the sun shine. But matter falling into a black hole's accretion disk can convert between 5.7% and 32% of its mass into pure energy before crossing the event horizon. That efficiency is terrifying. It means black holes extract more usable energy from matter than any other process in nature. And when you feed a black hole the mass of a sun every single day, the energy output becomes almost incomprehensible. Scientists recently solved one of the biggest mysteries about quasars: what ignites them. Detailed observations comparing 48 quasars with over 100 normal galaxies revealed the trigger. Quasars are born when galaxies collide. When two galaxies crash together, their gravitational dance pushes enormous amounts of gas toward the supermassive black holes at their centers. This isn't a gentle process. We're talking about hundreds of billions of stars and vast clouds of gas interacting over millions of years. The chaos funnels material inward, feeding the central black hole until it erupts into a quasar. Galaxies hosting quasars are 3 times more likely to show signs of recent collisions or interactions. The evidence is clear in their distorted shapes, their tidal tails of stars, their warped structures. Violence breeds power. More than 900,000 quasars have been catalogued as of 2023. They range from 600 million to 30 billion light-years away. The most distant ones show us the universe when it was young, when galaxies were still forming, when collisions were common. Looking at quasars is literally looking back in time to a more chaotic era of cosmic history. But here's where the competition gets interesting. Quasars are sustained powerhouses, shining continuously for millions of years. Other objects burst onto the scene with even more extreme, if brief, displays of power. Gamma-ray bursts are the most violent explosions the universe has produced since the Big Bang itself. They erupt without warning, flooding detectors with the highest energy light known to physics. A typical gamma-ray burst releases in mere seconds as much energy as our sun will generate across its entire 10 billion year lifespan. These aren't just bright, they're visible across almost the entire observable universe. When GRB 080319b detonated 7.5 billion light-years away, its optical counterpart reached magnitude 5.8. That's barely visible to the naked eye if you know exactly where to look. Except this star was halfway across the universe. The energy involved is staggering. If you assume the explosion radiates equally in all directions, GRB 080319b released energy within a factor of 2 of the sun's entire rest mass energy. That's the energy you'd get if you could somehow convert our sun entirely into radiation with perfect efficiency, holding nothing back. Gamma-ray bursts come in 2 flavors. Short bursts last less than 2 seconds and typically result from neutron stars colliding. Long bursts last from 2 seconds to over a minute and signal the birth of a black hole when a massive star collapses. On October 9th, 2022, detectors around the world and in orbit all lit up simultaneously. Something had just hammered our solar system with gamma radiation intense enough to overwhelm instruments designed to measure the most powerful events in space. The source, designated GRB221009a, turned out to be the brightest gamma-ray burst ever recorded. The gamma-ray emission lasted over 300 seconds. What makes gamma-ray bursts particularly interesting is that astronomers have been missing roughly half their total energy. Recent analysis suggests the energy in a burst's most intense gamma rays equals all its lower energy emissions combined. We've been undercounting their power this whole time. The mechanism behind long gamma-ray bursts involves hypernovae, stellar explosions an order of magnitude more powerful than regular supernovae. When a star more than 30 times the Sun's mass reaches the end of its life, it doesn't go quietly. The core collapses into a black hole, but the outer layers don't just fall in. Conservation of angular momentum causes the collapsing material to form a rapidly rotating disk around the newborn black hole. Jets of material blast outward from the poles at speeds approaching light itself, punching through the dying star and erupting into space. The first hypernova ever observed, SN 1998 BW, was 100 times more luminous than a standard supernova. It was also the first supernova definitively associated with a gamma-ray burst, confirming the connection between these extreme stellar deaths and the universe's most powerful explosions. Some hypernovae reach truly ridiculous extremes. ASASSN-15LH achieved a peak luminosity approximately 570 billion times that of our Sun. For comparison, that's 20 times brighter than all the light released by every star in the Milky Way combined. One exploding star, outshining an entire galaxy of hundreds of billions of stars. But hypernovae and gamma-ray bursts, while incredibly powerful, are brief. They flash brilliantly and fade. What about sustained power that isn't quite as intense as quasars, but operates on truly cosmic scales? Active galactic nuclei represent the broader category that includes quasars. AGNs are compact regions at galactic centers that emit tremendous energy not produced by stars. They're the most luminous persistent sources of electromagnetic radiation in the universe, ranging from relatively modest nearby examples emitting about 10 to the 40th power ergs per second to distant quasars pumping out more than 10 to the 47th power ergs per second. That's a range of 10 million times. The weakest AGN still produces 100 million times the Sun's power. The strongest outshines our Sun by a factor of 10 trillion. AGNs can outshine all the stars in their host galaxy by a factor of 100. Imagine that, a galaxy containing hundreds of billions of stars, and the tiny region at its core produces more light than all of them combined. Most galaxies probably harbor supermassive black holes at their centers. Some of those black holes actively feed, pulling in gas and dust. When they do, they become active galactic nuclei. The feeding process generates jets that can extend for over 1 million parsecs. That's more than 3 million light-years, dwarfing the galaxies themselves. Blazars represent a special subset of AGNs, where one of those jets points almost directly at Earth. This creates an illusion called superluminal motion, where features in the jet appear to move faster than light. Measurements of blazar jets have shown apparent speeds exceeding 25 times light speed. This isn't real faster-than-light travel. It's a geometric trick caused by material moving at 98% of light speed almost directly toward us, but it demonstrates the extreme velocities involved. These jets accelerate electrons, protons, and atomic nuclei to energies we can barely replicate in our most powerful particle accelerators. Blazars emit extremely high-energy gamma rays, light over 100 million times more energetic than the highest energy X-rays. The acceleration mechanisms in these jets remain partially mysterious, but numerical simulations support the possibility of accelerating protons to truly extreme energies. The jets themselves emit across all wavelengths simultaneously. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, all pouring out from a structure that can stretch across millions of light years, all ultimately powered by a supermassive black hole converting matter into energy with ruthless efficiency. Yet for all this power, for all these cosmic engines producing energies that make stars look dim, there's another class of object that operates on a completely different principle. These objects don't generate their power through accretion or nuclear fusion or matter-antimatter annihilation. They generate it through magnetism pushed to its absolute physical limit. Magnetars are neutron stars, the collapsed cores of dead massive stars, but with magnetic fields so intense they break the rules of normal matter. A typical neutron star has a magnetic field about 1 trillion times stronger than Earth's. A magnetar's field is 1,000 times stronger than that. We're talking about magnetic fields in excess of 10 to the 14th to 10 to the 15th Gauss. For perspective, that's 1 quadrillion times stronger than Earth's magnetic field. It's the strongest magnetic force ever observed in nature, and it's the most powerful magnetic object detected anywhere in the universe. The field is so intense it dictates the behavior of everything around it. It can twist and distort atoms, stretching them into elongated shapes that shouldn't exist. Hydrogen atoms in a magnetar's field are squashed about 200 times narrower than normal. The magnetic force overcomes electromagnetic repulsion, the fundamental force that normally keeps atoms their standard size. This extreme magnetism does something even stranger. It alters the vacuum of space itself. Empty space near a magnetar becomes birefringent, meaning light waves with different polarizations travel at different speeds. This is a property normally found in certain crystals on Earth, not in the vacuum of space. The magnetic field is so strong it changes the fundamental properties of nothingness. Over time, the crust of a magnetar becomes strained by the shifting magnetic field underneath. The field lines twist and writhe beneath the surface. Eventually, these stresses become too great. The crust cracks. What happens next is difficult to comprehend. These starquakes release titanic amounts of energy, sometimes 10 to the power of 46 ergs or more in a single outburst. That's more energy released in a fraction of a second than the sun produces in 100,000 years. The explosion can outshine the entire galaxy. On December 27th, 2004, astronomers witnessed one such spectacular blast from the magnetar SGR 1806-20. The burst of gamma rays was so intense, it partially ionized Earth's upper atmosphere. From halfway across the galaxy, the energy wave saturated NASA's Swift telescope detectors, instruments specifically designed to observe gamma-ray bursts. The spacecraft was essentially blinded by the intensity. At a distance of halfway from Earth to the Moon, roughly 192,000 kilometers, a magnetar could wipe information from the magnetic stripes of every credit card on Earth. At 1,000 kilometers, the magnetic field would be lethal, not through radiation, but through distortion. The field would warp the electron clouds of atoms in your body, rendering the chemistry of life impossible. Your molecules would simply stop functioning as molecules. These objects are only about 20 kilometers in diameter, 12 miles across. You could drive around one in less than an hour if you had a road, yet they pack more mass than our sun into that impossibly small volume. A tablespoon of magnetar material would weigh over 100 million tons. But magnetars represent steady-state power. constant, grinding magnetic energy that persists for thousands of years. There's another category of cosmic violence that operates on a completely different timescale. These events don't last for millennia. They last for seconds, maybe minutes at most. And in those brief moments, they outshine everything. Gamma-ray bursts are the most powerful explosions in the universe, not the most energetic over time, the most powerful per unit of time. These are short-lived outbursts of the highest energy light, and they can erupt with a quintillion times the luminosity of our Sun. That's a 1 followed by 18 zeros. Almost every day, somewhere in the cosmos, a gamma-ray burst occurs. Without warning, we detect them washing over Earth from distant galaxies. Each one signals something catastrophic. The cataclysmic birth of a black hole through either the collapse of a massive star or the merger of neutron stars. A typical gamma-ray burst releases as much energy in a few seconds as the Sun will produce in its entire 10 billion year lifetime. Think about that ratio. 10 billion years of solar output compressed into seconds. The explosion can be seen across almost the entirety of the visible universe. Astronomers classify gamma-ray bursts into two main types. Short bursts last less than 2 seconds. Long bursts last 2 seconds or more, typically about a minute. The mechanism differs between them. Short bursts come from neutron star mergers. Long bursts from the collapse of massive stars into black holes. But here's something researchers discovered recently. We've been missing about half the total energy. The gamma rays we detect, the highest energy photons, represent only part of the output. The energy in the most intense gamma rays is comparable to all the lower energy emissions combined. Previous measurements were systematically underestimating the true power of these events. GRB 080319b provides a stark example. This burst occurred 7.5 billion light-years away. Its optical counterpart, the visible light component, peaked at magnitude 5.8. That's comparable to the dimmest stars you can see with your naked eye. Except this wasn't a star. It was an explosion happening when the universe was roughly half its current age. If you'd been looking at the right spot in the sky at the right moment, you could have seen it without a telescope. A naked eye object from 7.5 billion light-years away. The energy output was staggering. Assuming a spherical explosion, GRB 080319b released energy within a factor of 2 of the rest mass energy of the Sun. That's the energy you'd get if you converted the entire mass of our Sun directly into radiation. E equals mc squared, taken to its logical extreme. Then came October 9th, 2022. An intense pulse of gamma radiation swept through our solar system. It overwhelmed detectors on numerous orbiting satellites. The source, designated GRB 221009A for its discovery date, turned out to be the brightest gamma-ray burst ever recorded. The gamma-ray emission lasted over 300 seconds, 5 minutes of reality-bending power. These events are both extremely energetic and extremely rare, a few per galaxy per million years. The sources are billions of light-years away, which tells us something profound about their intrinsic brightness. We're detecting them across cosmic distances that would render entire galaxies invisible. Yet these explosions shine through. Most energy is released in gamma rays, but some bursts have extremely luminous optical counterparts. The visible light alone can outshine billions of stars. The shock waves carry unimaginable kinetic energy. plowing through surrounding space at significant fractions of light speed. But gamma-ray bursts are transient, seconds to minutes of fury, then silence. There's another class of event that operates on longer timescales while releasing even more total energy. These aren't explosions in the traditional sense. They're eruptions, sustained outbursts powered by supermassive black holes feeding at unprecedented rates. In February 2020, astronomers announced the discovery of the Ophiuchus supercluster eruption, the most energetic event in the universe ever detected since the Big Bang. It occurred in the Ophiuchus cluster, in a galaxy designated Neve 1. The central supermassive black hole consumed nearly 270 million solar masses of material. That's 270 million suns worth of gas and dust falling into a black hole with a mass of 7 billion suns. The eruption lasted about 100 million years, not seconds, not minutes. 100 million years of sustained energy output. It released 5.7 million times more energy than the most powerful gamma-ray burst known. The shock waves and jets of high-energy particles punched a cavity in the intracluster medium, the hot gas between galaxies in the cluster. The cavity measures 1.5 million light-years wide, 10 times the diameter of the Milky Way. Imagine that scale. A hole in space carved by a single object's feeding frenzy. A void larger than 10 of our galaxies placed side by side. MS 0735 represents another example of extreme black hole feeding. Astronomers estimate the central black hole consumed mass equivalent to 300 million suns. That's as much mass as another supermassive black hole. The energy output was sufficient to create visible structures in the surrounding galaxy cluster, jets and cavities that will persist for billions of years, long after the feeding event has ended. These aren't just powerful events, they're universe-altering events. They shape the evolution of galaxy clusters. They regulate star formation across millions of light years. They inject energy and heavy elements into the space between galaxies. Without these violent outbursts, the large-scale structure of the cosmos would look completely different. But there's something even more extreme happening in the universe right now. Something that combines the sustained power of these eruptions with intensity that approaches gamma-ray burst levels. The fastest growing black hole known to date, J0529-4351. A quasar so luminous it defies comprehension. The central black hole has a mass of 17 billion suns, and it's feeding, consuming just over 1 solar mass per day. Every single day, this object swallows mass equivalent to our entire sun. The matter being pulled toward the black hole forms an accretion disk. As material spirals inward, it heats up through friction and compression. The disk emits so much energy that J0529-4351 is over 500 trillion times more luminous than the sun. The light took over 12 billion years to reach us. We're seeing this object as it was when the universe was less than 2 billion years old. This is the brightest persistent object in the known universe, not a brief explosion, not a short-lived outburst. Constant, sustained luminosity at levels that make galaxies look dim. More than 900,000 quasars have been discovered as of 2023. They range in distance from 600 million to 30 billion light-years away. Quasars emit radiation across the entire electromagnetic spectrum, from X-rays to the far infrared, with a peak in the ultraviolet optical bands. Some are strong radio sources. Some emit gamma rays. They can have luminosities between 10 and 100,000 times that of the Milky Way, generated from a region just a few light days to a few light years across. That's an area comparable in size to our solar system, producing more light than hundreds of billions of stars. Scientists recently unlocked one of the biggest mysteries about quasars. What triggers them? What causes a supermassive black hole to suddenly start feeding at these extreme rates? The answer: galaxy collisions. Researchers compared observations of 48 quasars and their host galaxies with images of over 100 non-quasar galaxies. The conclusion was clear. Galaxies hosting quasars are approximately 3 times as likely to be interacting or colliding with other galaxies. When two galaxies crash together, gravitational forces push enormous amounts of gas toward the supermassive black holes at the center of the remnant system. Just before that gas is consumed, it releases extraordinary amounts of energy as radiation. The result is a quasar. The power originates from the efficiency of the conversion process. Accretion disks around supermassive black holes can convert between 5.7% and 32% of an object's mass into energy. Compare that to the 0.7% efficiency of the nuclear fusion process that powers sun-like stars. Black hole accretion is up to 45 times more efficient than stellar fusion at converting mass to energy. This is why quasars can have the luminosity of 1 trillion stars contained in a space about the size of our solar system. The Milky Way hosts at least 100 billion stars spread across 100,000 light years. A quasar concentrates 10 times that luminosity into a region you could cross in a few years at light speed. Observations revealed that quasars radiate over 1 trillion times as much energy as our Sun from a region about the size of the solar system. The only mechanism capable of producing such enormous power is the conversion of gravitational energy into light by a massive black hole. Nothing else works. Nuclear fusion can't do it. Matter-antimatter annihilation could theoretically match it, but there's no plausible source of antimatter in sufficient quantities. The black hole explanation isn't just the best answer. It's the only answer that fits the observations, which tells us something remarkable about the universe. The most powerful persistent objects in existence derive their power from gravity, not from nuclear reactions, not from electromagnetic forces, from the warping of space-time itself around the most extreme objects nature allows. But there's another category of power in the universe that operates on a completely different principle. Quasars shine through sustained accretion. But what about objects whose power comes not from how much energy they emit, but from how intensely they can warp reality itself? Enter magnetars. These are neutron stars, the collapsed cores of massive stars that went supernova. About 20 kilometers in diameter, roughly 1.4 solar masses compressed into a sphere the size of a city. A tablespoon of magnetar material would have a mass of over 100 million tons. That density alone is extreme. But it's not the density that makes magnetars remarkable. It's the magnetic field. A magnetar's magnetic field reaches intensities between 10 to the 14th and 10 to the 15th Gauss. That's a quadrillion times stronger than Earth's magnetic field, 100 million times stronger than any magnet humans have ever created. As of 2020, magnetars are the most powerful magnetic objects detected anywhere in the universe. How strong is that field in practical terms? At a distance halfway between Earth and the Moon, roughly 192,000 kilometers away, a magnetar could wipe the magnetic information from every credit card on Earth, every hard drive, every magnetic storage device, erased from nearly 200,000 kilometers away. At 1,000 kilometers distance, the magnetic field would be lethal, not from radiation, from the field itself. The magnetic forces would distort the electron clouds in your atoms. Hydrogen atoms would be squashed 200 times narrower than normal. The chemistry that makes life possible would simply stop working. Your molecular bonds would fail. You would cease to exist as a coherent biological entity. The field alters the vacuum of space itself. Empty space near a magnetar becomes birefringent, splitting light into two polarization states like certain crystals do on Earth. The quantum vacuum, normally isotropic and uniform, becomes directional and structured. The magnetic field is so intense, it dictates how virtual particles pop in and out of existence. This isn't just strong magnetism. This is magnetism powerful enough to rewrite the rules of quantum field theory in its vicinity. Magnetars form when stars between 10 and 25 solar masses collapse. The compression during the collapse can supercharge any pre-existing magnetic field in the stellar core. The result is a field that's roughly 1,000 times stronger than a normal neutron star. And neutron stars already have magnetic fields billions of times stronger than anything on Earth. But the most spectacular displays of magnetar power come from starquakes. Over time, the magnetar's crust becomes strained. The magnetic field beneath the surface shifts and evolves. The crust, solid but under tremendous stress, eventually can't handle the strain. It cracks. And when it does, the energy release is staggering. A single starquake can release 10 to the 46 ergs of energy. That's more energy than the sun produces in 100,000 years, released in a fraction of a second. December 27th, 2004. The magnetar SGR 1806-20, located about 50,000 light-years away halfway across the galaxy, experienced a massive starquake. The burst of gamma rays that reached Earth was so intense, it partially ionized our upper atmosphere, from halfway across the Milky Way. The radiation overwhelmed detectors on multiple satellites, including NASA's SWIFT telescope, specifically designed to observe gamma-ray bursts. For a tenth of a second, this object became the brightest source of gamma rays in the sky, outshining every other object in the universe in that energy range. Despite being 50,000 light-years away, if SGR 1806-20 had been located just 10 light-years from Earth, the distance to some of our nearest stellar neighbors, that burst would have caused a mass extinction event. The radiation would have stripped away a significant portion of Earth's ozone layer. The aftermath would have been catastrophic for life on the surface. Magnetars demonstrate that power in the universe doesn't always come from size or luminosity. Sometimes it comes from intensity, from the concentration of fundamental forces into configurations so extreme they border on impossible. But even magnetars, for all their magnetic intensity, operate continuously. Their power output is constant, sustained over millions of years as they slowly spin down and their magnetic fields decay. What about events that release comparable energy in seconds? Gamma-ray bursts. These are the most powerful explosions in the universe since the Big Bang itself. Short-lived outbursts of the highest energy photons nature produces. They can erupt with a quintillion times the luminosity of our sun. That's a 1 followed by 18 zeros. A typical gamma-ray burst releases as much energy in a few seconds as the Sun will produce over its entire 10 billion year lifetime. Almost every day, somewhere in the observable universe, a gamma-ray burst occurs. We detect them as pulses of high-energy radiation, washing over Earth from random directions in the sky. Each one marks the birth of a black hole, either from the collapse of a massive star or from the merger of two neutron stars. Astronomers classify gamma-ray bursts into two categories based on duration. Short bursts last less than 2 seconds. Long bursts last 2 seconds or more, typically about a minute. The mechanism differs. Short bursts come from neutron star mergers. Long bursts come from collapsing massive stars, events called hypernovae. Because gamma-ray bursts originate billions of light-years away, the fact we can detect them at all tells you how powerful they are. These explosions can be seen across nearly the entire observable universe. Light from a gamma-ray burst can travel for 13 billion years and still be bright enough to trigger our instruments. The energy output is concentrated into two narrow jets. Material streaming out at 99.99% the speed of light, powered by the newborn black hole at the center. If you're in the path of one of those jets, you see a gamma-ray burst. If you're off to the side, you might see a supernova, or you might see nothing at all, depending on the angle. Recent observations revealed something unexpected. The energy in the most intense gamma rays from a burst is comparable to all the lower energy emissions combined. Astronomers had been missing roughly half the total energy output. The bursts are even more powerful than we thought. GRB 080319b, detected in 2008, was accompanied by an optical flash that peaked at magnitude 5.8. That's visible to the naked eye from 7.5 billion light-years away. If you had been looking at exactly the right spot in the sky at exactly the right moment, you could have seen this explosion with your unaided eyes, despite it occurring when the universe was barely half its current age. The energy output of GRB 080319b, assuming spherical emission, was within a factor of 2 of the total rest mass energy of the Sun. Essentially, if you converted the Sun's entire mass to energy, you'd get approximately the output of that single gamma-ray burst. Except the burst released it in seconds, not over 10 billion years. October 9th, 2022 brought GRB 221009a, the brightest gamma-ray burst ever recorded. Satellites across the solar system registered the event. The gamma-ray emission lasted over 300 seconds. The energy output was so extreme it saturated multiple detector systems designed to measure these events. Astronomers immediately recognized this as exceptional. GRB 221009a occurred relatively nearby by cosmic standards, about 2.4 billion light-years away. The combination of proximity and intrinsic brightness made it the most energetic electromagnetic event ever observed. But gamma-ray bursts, despite their extreme power, are brief, seconds or minutes. Then they fade. The afterglow can persist for days or weeks, but the main event is fleeting. There's something even more powerful, not in terms of instantaneous energy output, but in total energy released over time. The Ophiuchus supercluster eruption. February 2020. Astronomers announced the discovery of what remains the most energetic event ever detected in the universe since the Big Bang. It occurred in the Ophiuchus galaxy cluster, in a galaxy designated Neve 1. The cause was a supermassive black hole with a mass of about 7 billion solar masses. Over approximately 100 million years, this black hole accreted nearly 270 million solar masses of material. The energy released during this prolonged feeding frenzy created a cavity in the surrounding intracluster medium about 1.5 million light-years wide, 10 times the diameter of the Milky Way. The eruption released 5.7 million times more energy than the most powerful gamma-ray burst known, not in seconds, over millions of centuries, but the total energy budget exceeded anything else we've observed. The eruption sent shock waves and jets of particles tearing through the hot gas between galaxies in the cluster. It displaced enormous volumes of material. The cavity it carved out is visible in X-ray images as a dark region, a hole punched in the glowing gas that fills the space between galaxies. Similar events have been observed in other galaxy clusters. MS 0735 consumed an estimated 300 million solar masses. That's as much mass as another supermassive black hole. The energy required to move that much material, to carve out voids millions of light-years across, exceeds the total energy output of entire galaxies over billions of years. These cluster eruptions represent sustained power on scales that dwarf almost everything else. They're driven by the same mechanism as quasars, accretion onto supermassive black holes, but they operate over longer timescales and involve even more mass. Yet there's one more category of extreme power that deserves attention. Not the power to emit light or to warp space with magnetic fields, but the power to literally shake the fabric of space-time itself. Merging supermassive black holes. When two black holes with masses of 100 million solar masses each spiral into one another and merge, the final moment of coalescence releases gravitational waves. These ripples in space-time carry away enormous amounts of energy. In the last second before merger, the energy emitted as gravitational waves can be thousands of times greater than the combined electromagnetic output of every star in the observable universe. Thousands of times. In 1 second. This isn't light. It's not matter. It's not even radiation in the conventional sense. It's the geometry of space-time itself oscillating, carrying away the rotational energy of the merging black holes. The power output during that final second exceeds anything else in nature. But you can't see it with a telescope. You need gravitational wave detectors, instruments like LIGO and Virgo that measure the infinitesimal stretching and compressing of space as these waves pass through Earth. The waves from merging supermassive black holes are too low in frequency for current detectors. We can observe stellar mass black hole mergers, roughly 10 to 100 solar masses. Future space-based detectors like LISA will be able to detect the supermassive mergers. When they do, we'll be observing the most powerful events in the universe, not in electromagnetic radiation, in pure gravitational energy. Power in the universe comes in many forms: sustained luminosity from quasars, intense magnetic fields from magnetars, explosive gamma-ray bursts, prolonged eruptions from supermassive black holes, gravitational waves from merging compact objects. Each represents a different way the universe concentrates energy. Each pushes against the limits of what physics allows, and each reminds us that the cosmos operates at scales and intensities that challenge human comprehension. The universe doesn't just have one answer for most powerful. It has categories, distinctions that matter, Power measured by light output points to quasars. Power measured by magnetic intensity points to magnetars. Power measured by explosive energy release points to gamma-ray bursts. And power measured by gravitational wave emission points to merging black holes. But there's another dimension worth examining: sustained versus instantaneous power. Gamma-ray bursts release staggering amounts of energy, but they're over in seconds, maybe a few minutes for the longest ones. The power output during those brief moments exceeds almost anything else. But the total energy budget, integrated over time, might be less than what a quasar emits over years or centuries. Quasars sustain their luminosity for millions of years. They're beacons that shine across cosmic time. A quasar that radiates at 10 to the 47th power ergs per second for 1,000,000 years delivers far more total energy than a gamma-ray burst that lasts 30 seconds, even though the burst's peak power is higher. This distinction matters when comparing objects. Are we talking about peak power or total energy output? Peak power favors transient events, merging black holes in their final second. Gamma-ray bursts, hypernovae. Total energy favors sustained sources. Quasars, active galactic nuclei, the prolonged eruptions in galaxy clusters. Neither measure is more correct. They're different ways of quantifying power, and the universe produces extremes in both categories. Let's focus on one object that combines sustained power with extraordinary scale: the fastest growing black hole ever discovered. J0529-4351. This quasar holds the record for luminosity. It's the brightest object in the known universe, not the most powerful in terms of peak energy release, but the brightest steady source we've observed. The black hole at its center has a mass of 17 billion solar masses. That alone places it among the most massive black holes known. But mass isn't what makes it remarkable. It's the feeding rate. This black hole consumes more than 1 solar mass per day. Every day, it swallows material equivalent to our entire sun. The accretion disk surrounding it glows so intensely that the quasar outshines everything else. J0529-4351 is over 500 trillion times more luminous than the sun. Let that number settle. 500 quadrillion times brighter than the star that lights our world. From an object roughly the size of our solar system, the light from this quasar has traveled for over 12 billion years to reach us. We're seeing it as it was when the universe was less than 2 billion years old, shortly after the first galaxies formed. Yet even across that vast distance, across billions of light years of expanding space, it's still the brightest thing we've detected. This raises an obvious question. How did such a massive black hole grow so quickly in the early universe? We don't have a complete answer. Black holes this large shouldn't exist so soon after the Big Bang, at least not according to standard growth models. A black hole grows by accreting matter, but accretion has limits. When matter falls onto a black hole, it heats up, it radiates. That radiation creates outward pressure. Radiation pressure pushes against infalling material. This creates a natural limit called the Eddington limit. A black hole can only grow so fast before its own luminosity prevents additional matter from falling in. The radiation blows away the surrounding gas. For J0529-4351 to reach 17 billion solar masses in less than 2 billion years requires accretion rates near or above the Eddington limit for extended periods. That's theoretically possible, but rare. And it doesn't fully explain how the seed black hole formed in the first place. Some models propose that the early universe had conditions favoring rapid black hole growth: dense gas clouds, high merger rates, less feedback from stellar winds. But we're still working out the details. What we do know is that J0529-4351 exists, and it's feeding voraciously. The accretion disk converts mass to energy with extraordinary efficiency. Between 5.7% and 32% of the infalling mass gets converted to radiation, depending on the black hole's spin and the disk's properties. Nuclear fusion in stars converts about 0.7% of mass to energy. Accretion onto black holes is far more efficient. It's the most efficient energy conversion process in nature, aside from matter-antimatter annihilation. This efficiency is why quasars can outshine entire galaxies. The black hole at the center of a quasar might be millions or billions of solar masses, but the accretion disk is relatively small, just light days to light years across, yet it produces more light than hundreds of billions of stars. The power comes from gravitational energy. Matter falling into a black hole releases its gravitational potential energy. That energy heats the accretion disk to millions of degrees, hot enough to emit X-rays and ultraviolet light. The disk doesn't just glow, it launches jets, streams of particles accelerated to near light speed. These jets extend for millions of light years in some cases. They punch through the surrounding gas, creating enormous bubbles and cavities. Quasars were common in the early universe. More than 900,000 have been catalogued. Most are billions of light years away. We're seeing them as they were when the universe was young. Today, quasars are rarer. Most supermassive black holes have consumed the available gas in their vicinity. They're dormant, quiet. The Milky Way's central black hole falls into this category. Sagittarius A star is massive but currently inactive. It's not feeding at rates that produce quasar-level luminosity, but quasars can be reawakened. When galaxies collide, gravitational forces funnel gas toward the central black holes. This can trigger a new phase of accretion, a new quasar. Observations show that galaxies hosting quasars are about 3 times more likely to be interacting or colliding with other galaxies. The connection between galaxy mergers and quasar activity is well established. This tells us something important. The most powerful sustained objects in the universe are triggered by cosmic violence. Galaxies don't produce quasars in isolation. They need disruption, interaction. The chaos of collision funnels fuel to the black hole. Without that fuel supply, even the most massive black holes remain dark. J0529-4351 is likely the product of such processes. Its host galaxy probably experienced multiple mergers. Each merger delivered fresh gas to the central black hole. Each accretion event increased the black hole's mass and luminosity. And the cycle continues. As long as gas keeps falling in, the quasar keeps shining. But even J0529-4351 won't last forever. Eventually, the gas supply will deplete. The accretion rate will drop. The luminosity will fade. The black hole will enter a quiet phase, like Sagittarius A star. This raises another question. What was the most luminous quasar that ever existed? We can only observe quasars whose light has reached us. There could be even brighter quasars at distances so great their light hasn't arrived yet. or quasars that existed briefly and faded before we could detect them. The universe is 13.8 billion years old. We can only see objects whose light has had time to cross space and reach our telescopes. This creates an observational horizon. Beyond that horizon, there are regions of the universe we can never observe. Not because they don't exist, but because the light hasn't had time to travel the distance. Some of those regions might host quasars even more luminous than J0529-4351. We'll never know. This limitation applies to all astronomy. We're constrained by the speed of light and the age of the universe. But within the observable universe, J0529-4351 currently holds the record, and it's a worthy champion. Its luminosity dwarfs everything else we've catalogued. It represents the extreme end of sustained power, a black hole feeding at maximum capacity, converting mass to light with ruthless efficiency. Yet even this extraordinary object has competition in different categories of power. If we shift from electromagnetic radiation to other forms of energy, different objects take the lead. Magnetars dominate magnetic field strength. Gamma-ray bursts dominate explosive energy release. Merging black holes dominate gravitational wave emission. And then there are objects that combine multiple extremes. Blazars, for instance. A blazar is a quasar with its jet pointed directly at us. The relativistic jet, traveling at nearly light speed, is aimed straight at Earth. This creates an effect called relativistic beaming. When a jet moves toward you at close to light speed, its radiation gets concentrated in the forward direction. The light gets compressed, blue-shifted, amplified. What you see is far brighter than if the jet were pointed elsewhere. Blazars can appear extraordinarily luminous, not because they're intrinsically more powerful than other quasars, but because the geometry favors our line of sight. But some blazars are genuinely extreme. They emit gamma rays at energies exceeding 100 billion electron volts. That's light more than 100 million times more energetic than medical X-rays. These high-energy photons are created when particles in the jet collide with lower energy photons. The collisions boost the photon energies to extreme levels. Blazars also exhibit superluminal motion. Features in the jet appear to move faster than light across the sky. This is an illusion caused by the jet's orientation and speed. The material isn't actually exceeding light speed, but the apparent motion can be 25 times faster than light. The true speed is typically above 98% of light speed. Close enough to the cosmic speed limit that relativistic effects dominate. Blazars challenge our instruments. Their gamma-ray emissions are so intense they can saturate detectors designed to observe the highest energy events in the universe. They're also variable. Blazar luminosity can change on timescales of hours or days. The jet's activity fluctuates. The particle acceleration varies. The radiation output surges and drops. This variability tells us something about the jet's structure. The emitting region must be compact. If the gamma rays came from a region light years across, we wouldn't see fluctuations on hour-long timescales. Light travel time would smooth out the variations. But if the emitting region is only light hours or light days across, rapid changes are possible. The jet can vary quickly because the entire emitting zone can respond coherently. This makes blazars useful probes of black hole physics. By watching how quickly the luminosity changes, we can infer the size and structure of the jet. We can study particle acceleration in extreme magnetic fields. We can test theories of relativistic plasma behavior. And we can appreciate that the universe contains objects capable of accelerating particles to energies we can barely reproduce in our largest colliders. The jets from supermassive black holes are cosmic particle accelerators operating at scales and powers we can't match. Some blazars are also neutrino sources. Neutrinos are ghostly particles that rarely interact with matter. They pass through planets, stars, even entire galaxies without stopping. But occasionally, a neutrino will collide with an atom in a detector buried deep underground or under Antarctic ice. When that happens, we can trace the neutrino back to its source. In 2017, a neutrino detected by IceCube, a detector embedded in Antarctic ice, was traced to a blazar called TXS 0506 plus 056. This was the first time a high-energy neutrino was conclusively linked to a specific cosmic source. It confirmed that blazars produce not just gamma rays, but also neutrinos. The particle acceleration in the jet is so extreme it creates neutrinos with energies far exceeding anything from the Sun or other normal stars. This multi-messenger astronomy, combining light, gravitational waves, and neutrinos, opens new ways to study the most powerful objects. Each messenger carries different information. Light tells us about temperature and composition. Gravitational waves tell us about space-time distortion. Neutrinos tell us about particle interactions in extreme environments. Together, they reveal a universe far more dynamic and violent than visible light alone suggests. And they confirm what the numbers already told us. The most powerful objects in the universe operate at energy scales that dwarf human experience. They challenge our instruments. They push against theoretical limits. They remind us that the cosmos is not a gentle place. Power in the universe is not evenly distributed. Most of space is cold, dark, nearly empty. But in rare locations, under specific conditions, energy concentrates. Black holes form, jets launch, magnetic fields amplify, explosions occur. These rare events and objects dominate the energy budget of the universe. They shape galactic evolution. They enrich the interstellar medium with heavy elements. They trigger star formation. They regulate gas flows across cosmic scales. Without quasars, without gamma-ray bursts, without supernovae and magnetars and all the other extreme phenomena, galaxies would evolve differently. Structure formation would follow different pathways. The universe would look different. The most powerful objects aren't just interesting curiosities. They're essential players in cosmic history, and they define what's possible in the universe. Now, you're probably wondering something. If black holes and their jets dominate the power rankings, what about other extreme objects? What about the densest stars? What about magnetic fields so strong they warp the fabric of reality itself? Enter magnetars. Magnetars are neutron stars, but calling them that is like calling a supernova a bright light. They're neutron stars with magnetic fields so powerful they redefine what we mean by strong. A typical neutron star has a magnetic field about 1 trillion times stronger than Earth's. Already absurd, already beyond human scale. A magnetar multiplies that by another 1,000. The numbers become almost meaningless. A magnetar's magnetic field reaches 10 to the 14th Gauss, sometimes 10 to the 15th. That's a quadrillion times stronger than Earth's field. The strongest magnetic field humans have ever created in a laboratory peaks around 1 million Gauss. A magnetar's field is 100 million times stronger than that. What does a field like that actually do? It distorts atoms. Hydrogen, the simplest element, gets compressed to a fraction of its normal width. The electron orbits stretch and deform under the magnetic stress. Chemistry as we know it stops working. At a distance of 1,000 kilometers, a magnetous field would be lethal. Not because of radiation, though there's plenty of that, because the magnetic field itself would tear apart the electron clouds in your atoms. The biochemistry that keeps you alive would simply cease to function. Closer in, things get stranger. The magnetic field becomes so intense it affects the vacuum of space. Empty space, under normal conditions, is isotropic. Light travels the same speed in all directions. But near a magnetar, the vacuum becomes birefringent. Light polarized in different directions travels at different speeds. Space itself develops properties we normally associate with crystals. This isn't theoretical. We've measured it. The power output of a magnetar doesn't come from fusion. Neutron stars don't fuse anything. Their cores are too dense. Instead, magnetars get their energy from their magnetic fields. As the field decays over thousands of years, it releases energy. The star's crust, under immense strain from the shifting field lines, occasionally cracks. These are called starquakes. The name sounds almost gentle. It's not. A typical starquake on a magnetar releases more energy in a fraction of a second than the Sun produces in 100,000 years. That's 10 to the 46th ergs. To put that in perspective, if you could somehow convert a single kilogram of matter entirely into energy, you'd get about 10 to the 21st ergs. A magnetar starquake releases energy equivalent to converting 10 billion trillion kilograms of matter into pure radiation in a tenth of a second. December 27, 2004, a magnetar called SGR 1806-20 had one of these outbursts. The gamma-ray pulse was so intense, it saturated detectors on satellites designed specifically to measure gamma-ray bursts. The pulse traveled 50,000 light-years across the galaxy. When it hit Earth's upper atmosphere, it partially ionized the ionosphere. From halfway across the Milky Way, a stellar object the size of a city temporarily disrupted our planet's atmospheric chemistry. If that magnetar had been 10 light-years away instead of 50,000, the burst would have triggered a mass extinction. Magnetars exist because of how neutron stars form. When a massive star collapses, conservation of angular momentum spins up the core. Conservation of magnetic flux amplifies the field. If the original star had even a modest magnetic field, the collapse concentrates it. The field lines, frozen into the stellar material, compress along with everything else. The result is a star 20 kilometers across with a mass 1.4 times the Sun. The density is so extreme that a teaspoon of neutron star material would weigh 100 million tons on Earth. The magnetic field threading through this ultra-dense matter reaches levels that simply don't exist anywhere else in nature. The field energy alone contributes measurably to the star's gravitational mass. But here's what makes magnetars particularly interesting for our discussion about power. They're not the most luminous objects. Quasars outshine them by enormous margins. They're not the most energetic events. Gamma-ray bursts release more total energy. But magnetars have the strongest magnetic fields ever measured in the universe. And magnetic fields are a form of power. They can accelerate particles. They can store energy. They can do work across vast distances. A magnetar sitting in empty space doesn't just radiate. It creates a magnetosphere extending thousands of kilometers outward. Any charged particle entering that region gets accelerated to relativistic speeds. The field lines twist and snap, releasing bursts of X-rays and gamma rays. The star essentially becomes a particle accelerator, operating continuously for millennia. This matters for how we think about power distribution in the universe. Quasars and blazars represent one mode, accretion onto supermassive black holes, converting gravitational potential energy into radiation and kinetic energy of jets. Gamma-ray bursts represent another, explosive events releasing stored energy all at once. Magnetars represent a third mode, sustained power from magnetic field decay. It's a different mechanism entirely. No accretion disk, no jet, just a magnetic field so strong it dominates the local environment and radiates energy as it slowly unwinds. And here's something you might not expect. Magnetars probably aren't that rare. We've found about 30 confirmed magnetars in the Milky Way. But our galaxy is big, and magnetars are hard to detect unless they're actively flaring. The estimated population could be tens of thousands, maybe more. They form whenever a sufficiently massive star collapses with the right properties. Given how many massive stars exist, magnetar formation should be relatively common, which means the universe contains countless stellar objects with magnetic fields strong enough to distort atoms and alter the properties of space-time itself. Most of them sit quietly, slowly radiating away their magnetic energy over 10,000 years. Occasionally, one cracks, releasing a burst of gamma rays that briefly outshines entire galaxies. Then it fades back into relative obscurity. This is the pattern we keep seeing. Power in the universe concentrates, black holes accrete, magnetic fields amplify, stars explode. But these events are temporary or localized. The universe as a whole remains relatively calm. Most of space is empty. Most of time passes without drama. But when energy does concentrate, when conditions align, the results are spectacular. Magnetars also connect to another class of extreme events. When two neutron stars orbit each other, they gradually spiral inward, losing energy to gravitational waves. Eventually, they merge. The collision releases a kilonova, an explosion about 1,000 times brighter than a classical nova. The merger also produces a gamma-ray burst, typically a short one lasting a few seconds, and it creates heavy elements. Neutron-rich matter ejected during the collision undergoes rapid neutron capture. Elements beyond iron form in this process: gold, platinum, uranium, the iodine in your thyroid, the gold in any jewelry you own. Most of the heaviest elements on Earth came from neutron star mergers billions of years ago, before the solar system formed. The August 2017 detection of gravitational waves from merging neutron stars confirmed this. LIGO and Virgo detected the gravitational signal. Telescopes around the world observed the kilonova. Spectroscopy of the explosion showed signatures of heavy element formation. For the first time, we watched the universe create gold in real time. Well, real time delayed by 130 million years. The merger happened in a galaxy called NGC 4993. The light and gravitational waves traveled for 130 million years before reaching Earth. But when they arrived, we caught them. We measured them. We learned. The power released in that final second before merger is staggering. 2 neutron stars, each about 1.4 solar masses, spiraling together at a significant fraction of light speed. The gravitational waves they emit carry away energy. In the last second, They radiate more power than all the stars in the visible universe combined. Let that settle for a moment. All the stars in the observable universe, hundreds of billions of galaxies, each containing hundreds of billions of stars, fusing hydrogen, radiating light. The combined output is enormous, but in the final second, before two neutron stars merge, their gravitational wave emission exceeds that combined stellar output by orders of magnitude. This is power on a scale that makes stellar fusion look insignificant, and it happens in a region of space smaller than a city. The densities involved are beyond extreme. The energies are incomprehensible. The physics pushes against the limits of general relativity. After the merger, what's left? Sometimes another neutron star, more massive than either progenitor. Sometimes a black hole, depends on the total mass. If the remnant exceeds about 2.5 solar masses, collapse to a black hole is inevitable. Nothing can support that much mass in such a small volume. If a massive neutron star forms, it might be a magnetar. The magnetic fields from both progenitor stars, twisted and amplified during the merger, could produce a field even stronger than normal magnetars. These merger remnants might be the strongest magnets in the universe. We haven't confirmed this directly. The objects are distant. The afterglows fade quickly. But the theoretical models suggest it's possible, maybe even likely. Which means some of the magnetars we observe today could be merger remnants. Neutron stars that came from the collision of two other neutron stars. The universe recycles its extremes. This brings us back to a central theme. The most powerful objects and events in the universe are connected. Massive stars create neutron stars and black holes. Neutron stars merge, creating heavy elements and possibly more neutron stars. Black holes accrete, launching jets that shape galaxies. Galaxies collide, funneling gas into their central black holes, igniting quasars. It's a cycle. Not a perfect loop, but a network of cause and effect spanning cosmic timescales. The power we observe today came from processes that began billions of years ago. The explosions we detect across the universe are consequences of stellar evolution, of gravitational dynamics, of quantum mechanics operating under extreme conditions, and all of it follows from the same basic physics: general relativity, thermodynamics, electromagnetism, the strong and weak nuclear forces. No new laws needed. Just the same principles we test in laboratories, applied to regimes where gravity is strong, densities are extreme, and energies reach levels we can barely produce in colliders. The universe is consistent. The laws don't change based on scale. A magnetar's field follows Maxwell's equations. A neutron star merger follows Einstein's field equations. The particle acceleration in a blazar jet follows the Lorentz force law. We can describe it all with mathematics developed on Earth, tested in controlled environments, extended to cosmic extremes. That's worth appreciating. The most powerful objects in the universe aren't mysterious in principle. We understand the physics. We can calculate the energies. We can predict the outcomes. The challenge isn't the physics, it's the scale. A magnetar's field is strong, but we know how magnetic fields work. A gamma-ray burst is energetic, but we know how shock waves accelerate particles. A quasar is luminous, but we know how accretion disks radiate. The mechanisms are known. The equations are solved. The mystery is gone. What remains is awe. Because understanding something doesn't make it less impressive. Knowing how a magnetar generates its field doesn't reduce the fact that it's a quadrillion times stronger than Earth's. Calculating the energy output of a quasar doesn't change that it outshines a trillion stars. Measuring a gamma-ray burst doesn't diminish the fact that it releases more energy in seconds than the Sun will in its entire lifetime. The numbers speak for themselves, and the numbers are extraordinary, and they define what's possible in the universe. Now you're probably wondering something. If black holes and their jets dominate the power rankings, what about other extreme objects? What about the densest stars? What about magnetic fields so strong they warp the fabric of reality itself? Enter magnetars. Magnetars are neutron stars, but calling them that is like calling a supernova a bright light. They're neutron stars with magnetic fields so powerful they redefine what we mean by strong. A typical neutron star has a magnetic field about 1 trillion times stronger than Earth's. Already absurd. Already beyond human scale. A magnetar multiplies that by another 1,000. The numbers become almost meaningless. A magnetar's magnetic field reaches 10 to the 14th Gauss, sometimes 10 to the 15th. That's a quadrillion times stronger than Earth's field. The strongest magnetic field humans have ever created in a laboratory peaks around 1 million Gauss. A magnetar's field is 100 million times stronger than that. What does a field like that actually do? It distorts atoms. Hydrogen, the simplest element, gets compressed to a fraction of its normal width. The electron orbits stretch and deform under the magnetic stress. Chemistry as we know it stops working. At a distance of 1,000 kilometers, a magnetar's field would be lethal. Not because of radiation, though there's plenty of that, because the magnetic field itself would tear apart the electron clouds in your atoms. The biochemistry that keeps you alive would simply cease to function. Closer in, things get stranger. The magnetic field becomes so intense it affects the vacuum of space. Empty space, under normal conditions, is isotropic. Light travels the same speed in all directions. But near a magnetar, the vacuum becomes birefringent. Light polarized in different directions travels at different speeds. Space itself develops properties we normally associate with crystals. This isn't theoretical. We've measured it. The power output of a magnetar doesn't come from fusion. Neutron stars don't fuse anything. Their cores are too dense. Instead, magnetars get their energy from their magnetic fields. As the field decays over thousands of years, it releases energy. The star's crust, under immense strain from the shifting field lines, occasionally cracks. These are called starquakes. The name sounds almost gentle. It's not. A typical starquake on a magnetar releases more energy in a fraction of a second than the Sun produces in 100,000 years. That's 10 to the 46th ergs. To put that in perspective, if you could somehow convert a single kilogram of matter entirely into energy, you'd get about 10 to the 21st ergs. A magnetar starquake releases energy equivalent to converting 10 billion trillion kilograms of matter into pure radiation in 1/10 of a second. December 27th, 2004, a magnetar called SGR 1806-20 had one of these outbursts. The gamma-ray pulse was so intense it saturated detectors on satellites designed specifically to measure gamma-ray bursts. The pulse traveled 50,000 light-years across the galaxy. When it hit Earth's upper atmosphere, it partially ionized the ionosphere. From halfway across the Milky Way, a stellar object the size of a city temporarily disrupted our planet's atmospheric chemistry. If that magnetar had been 10 light-years away instead of 50,000, the burst would have triggered a mass extinction. Magnetars exist because of how neutron stars form. When a massive star collapses, conservation of angular momentum spins up the core. Conservation of magnetic flux amplifies the field. If the original star had even a modest magnetic field, the collapse concentrates it. The field lines, frozen into the stellar material, compress along with everything else. The result is a star 20 kilometers across with a mass 1.4 times the Sun. The density is so extreme that a teaspoon of neutron star material would weigh 100 million tons on Earth. The magnetic field threading through this ultra-dense matter reaches levels that simply don't exist anywhere else in nature. The field energy alone contributes measurably to the star's gravitational mass. But here's what makes magnetars particularly interesting for our discussion about power. They're not the most luminous objects. Quasars outshine them by enormous margins. They're not the most energetic events. Gamma-ray bursts release more total energy. But magnetars have the strongest magnetic fields ever measured in the universe. And magnetic fields are a form of power. They can accelerate particles, they can store energy, they can do work across vast distances. A magnetar sitting in empty space doesn't just radiate. It creates a magnetosphere extending thousands of kilometers outward. Any charged particle entering that region gets accelerated to relativistic speeds. The field lines twist and snap, releasing bursts of X-rays and gamma rays. The star essentially becomes a particle accelerator, operating continuously for millennia. This matters for how we think about power distribution in the universe. Quasars and blazars represent one mode: accretion onto supermassive black holes, converting gravitational potential energy into radiation and kinetic energy of jets. Gamma-ray bursts represent another: explosive events releasing stored energy all at once. Magnetars represent a third mode: sustained power from magnetic field decay. It's a different mechanism entirely. No accretion disk, no jet, just a magnetic field so strong it dominates the local environment and radiates energy as it slowly unwinds. And here's something you might not expect. Magnetars probably aren't that rare. We've found about 30 confirmed magnetars in the Milky Way, but our galaxy is big, and magnetars are hard to detect unless they're actively flaring. The estimated population could be tens of thousands, maybe more. They form whenever a sufficiently massive star collapses with the right properties. Given how many massive stars exist, magnetar formation should be relatively common, which means the universe contains countless stellar objects with magnetic fields strong enough to distort atoms and alter the properties of space-time itself. Most of them sit quietly, slowly radiating away their magnetic energy over 10,000 years. Occasionally, one cracks, releasing a burst of gamma rays that briefly outshines entire galaxies. Then it fades back into relative obscurity. This is the pattern we keep seeing. Power in the universe concentrates. Black holes accrete. Magnetic fields amplify. Stars explode. But these events are temporary or localized. The universe as a whole remains relatively calm. Most of space is empty. Most of time passes without drama. But when energy does concentrate, when conditions align, the results are spectacular. Magnetars also connect to another class of extreme events. When two neutron stars orbit each other, they gradually spiral inward, losing energy to gravitational waves. Eventually, they merge. The collision releases a kilonova, an explosion about 1,000 times brighter than a classical nova. The merger also produces a gamma-ray burst, typically a short one lasting a few seconds, and it creates heavy elements. Neutron-rich matter ejected during the collision undergoes rapid neutron capture. Elements beyond iron form in this process: gold, platinum, uranium. The iodine in your thyroid, the gold in any jewelry you own. Most of the heaviest elements on Earth came from neutron star mergers billions of years ago, before the solar system formed. The August 2017 detection of gravitational waves from merging neutron stars confirmed this. LIGO and Virgo detected the gravitational signal. Telescopes around the world observed the kilonova. Spectroscopy of the explosion showed signatures of heavy element formation. For the first time, we watched the universe create gold in real time. Well, real time delayed by 130 million years. The merger happened in a galaxy called NGC 4993. The light and gravitational waves traveled for 130 million years before reaching Earth. But when they arrived, we caught them, we measured them, we learned. The power released in that final second before merger is staggering. 2 neutron stars, each about 1.4 solar masses, spiraling together at a significant fraction of light speed. The gravitational waves they emit carry away energy. In the last second, they radiate more power than all the stars in the visible universe combined. Let that settle for a moment. All the stars in the observable universe, hundreds of billions of galaxies, each containing hundreds of billions of stars, fusing hydrogen, radiating light. The combined output is enormous. But in the final second before 2 neutron stars merge, their gravitational wave emission exceeds that combined stellar output by orders of magnitude. This is power on a scale that makes stellar fusion look insignificant. And it happens in a region of space smaller than a city. The densities involved are beyond extreme. The energies are incomprehensible. The physics pushes against the limits of general relativity. After the merger, what's left? Sometimes another neutron star, more massive than either progenitor. Sometimes a black hole. Depends on the total mass. If the remnant exceeds about 2.5 solar masses, collapse to a black hole is inevitable. Nothing can support that much mass in such a small volume. If a massive neutron star forms, it might be a magnetar. The magnetic fields from both progenitor stars, twisted and amplified during the merger, could produce a field even stronger than normal magnetars. These merger remnants might be the strongest magnets in the universe. We haven't confirmed this directly. The objects are distant. The afterglows fade quickly, but the theoretical models suggest it's possible, maybe even likely, which means some of the magnetars we observe today could be merger remnants. Neutron stars that came from the collision of 2 other neutron stars. The universe recycles its extremes. This brings us back to a central theme. The most powerful objects and events in the universe are connected. Massive stars create neutron stars and black holes. Neutron stars merge, creating heavy elements and possibly more neutron stars. Black holes accrete, launching jets that shape galaxies. Galaxies collide, funneling gas into their central black holes, igniting quasars. It's a cycle, not a perfect loop, but a network of cause and effect spanning cosmic timescales. The power we observe today came from processes that began billions of years ago. The explosions we detect across the universe are consequences of stellar evolution, of gravitational dynamics, of quantum mechanics operating under extreme conditions. and all of it follows from the same basic physics: general relativity, thermodynamics, electromagnetism, the strong and weak nuclear forces. No new laws needed, just the same principles we test in laboratories, applied to regimes where gravity is strong, densities are extreme, and energies reach levels we can barely produce in colliders. The universe is consistent. The laws don't change based on scale. A magnetar's field follows Maxwell's equations. A neutron-star merger follows Einstein's field equations. The particle acceleration in a blazar jet follows the Lorentz force law. We can describe it all with mathematics developed on Earth, tested in controlled environments, extended to cosmic extremes. That's worth appreciating. The most powerful objects in the universe aren't mysterious in principle. We understand the physics. We can calculate the energies. We can predict the outcomes. The challenge isn't the physics, it's the scale. A magnetar's field is strong, but we know how magnetic fields work. A gamma-ray burst is energetic, but we know how shock waves accelerate particles. A quasar is luminous, but we know how accretion disks radiate. The mechanisms are known. The equations are solved. The mystery is gone. What remains is awe. Because understanding something doesn't make it less impressive. Knowing how a magnetar generates its field doesn't reduce the fact that it's a quadrillion times stronger than Earth's. Calculating the energy output of a quasar doesn't change that it outshines a trillion stars. Measuring a gamma-ray burst doesn't diminish the fact that it releases more energy in seconds than the sun will in its entire lifetime. The numbers speak for themselves, and the numbers are extraordinary. The universe doesn't just produce powerful objects, it produces observers capable of measuring them. That's the real miracle. Every instrument we've built, every detector we've launched, every telescope we've aimed at the sky is a product of stellar nucleosynthesis. The silicon in our chips, the aluminum in our spacecraft, the gold in our connectors, all forged in stellar cores or neutron star mergers. We're using the products of cosmic violence to study cosmic violence. That feedback loop is profound. The universe created the elements necessary for complex chemistry. Complex chemistry produced life. Life evolved intelligence. Intelligence developed technology. Technology measures the processes that created the technology. We're inside the system we're studying. Not external observers, but participants. The atoms in your brain contemplating magnetars were once inside stars. The calcium in your bones clicking a mouse to view gamma-ray burst data came from supernova explosions. You're not separate from these cosmic phenomena. You're made of them. This changes the nature of the question. We're not asking, what's the most powerful object in the universe, from outside? We're asking it from within. As arrangements of atoms that once participated in these very processes, that perspective matters. Because power isn't just about energy output. It's about consequences, about impact, about what changes because the object exists. A gamma-ray burst releases extraordinary energy, but it's brief, seconds or minutes. Then it's over. The radiation propagates outward at light speed, thinning as it expands. After a few thousand years, it's undetectable. A magnetar maintains its field for thousands of years, maybe millions. The energy isn't released in one burst, but sustained over geological timescales. Different kind of power, same fundamental physics. A quasar shines for millions or billions of years. Steady, relentless output. Not the brief spike of a gamma-ray burst, but sustained luminosity that shapes galactic evolution. The radiation pressure from a quasar can shut down star formation across an entire galaxy. It can drive gas out of the galactic core, starving the central black hole, eventually shutting itself off. That's negative feedback. The quasar's power regulates its own fuel supply. Too much output, too much radiation pressure, gas gets expelled, accretion rate drops, luminosity decreases, equilibrium. The universe self-regulates even at these extremes. Black hole mergers are different again. Singular events, two massive objects spiraling together over millions of years, then merging in seconds. The gravitational wave output during that final merger exceeds the electromagnetic luminosity of all stars in the observable universe, but only for a fraction of a second. Which is more powerful, the brief but incomprehensible spike, or the sustained output over cosmic timescales? The answer depends on what you're measuring. Peak luminosity favors the merger. Total energy output might favor the quasar. Impact on surrounding environment could go either way. There's no single metric that captures power completely. We can measure energy per second, energy per unit mass, energy per unit volume, magnetic field strength, gravitational potential. Each metric gives a different answer. Magnetars win on magnetic field strength. Nothing else comes close. But their total energy output is lower than quasars. Quasars win on sustained luminosity, but their peak output is lower than gamma-ray bursts. Gamma-ray bursts win on brief luminosity, but their total lifetime energy is less than a quasar's. Black hole mergers win on gravitational wave output, but that's a different kind of radiation, not electromagnetic, not directly observable until recently. The Ophiuchus supercluster eruption released more total energy than any gamma-ray burst, by a factor of millions. But it took 100 million years. The energy was spread out over time, less intense, more sustained. So the question fragments. Most powerful becomes most powerful at what? Most luminous, most energetic per second, most total energy, strongest field, deepest gravitational well. Each has a different answer, and each answer is correct within its context. But there's another angle. Power relative to size. Quasars emit incredible luminosity from a region the size of the solar system. That's compact. But neutron stars pack similar mass into a sphere 20 kilometers across. That's density. That's concentration. A black hole's event horizon is smaller still. All the mass compressed to a point, classically. Quantum gravity probably prevents a true singularity, but the scale is still subatomic. Everything inside the event horizon. All the information, all the mass, all the angular momentum, contained within a boundary measured in kilometers for stellar mass black holes, or solar system scales for supermassive ones. That concentration of spacetime curvature is extreme. Nothing curves spacetime more severely. The gradient near the event horizon is the steepest possible without creating a naked singularity, which the cosmic censorship hypothesis suggests doesn't happen. So black holes might win on spacetime curvature, magnetars on field strength, quasars on sustained luminosity, gamma-ray bursts on peak electromagnetic output, black hole mergers on gravitational wave luminosity. No single winner, just different categories of extreme, and all of it observable, detectable, measurable. We've built instruments sensitive enough to detect these phenomena across billions of light years. gravitational wave detectors that measure distortions smaller than the width of a proton, X-ray telescopes that resolve emission from accretion disks around black holes, radio arrays that image jets from quasars. The technology required to observe these objects is itself remarkable. Interferometry, adaptive optics, space-based detectors above the atmosphere, cryogenic sensors cooled to millikelvin temperatures. We've constructed machines that operate at the quantum limit of measurement. Gravitational wave detectors limited by quantum fluctuations in their mirrors. Radio receivers cooled until thermal noise is minimized. Photon counters that register individual gamma rays. The engineering required to detect the universe's most powerful objects pushes our technology to fundamental limits. Limits set by quantum mechanics, by thermodynamics, by the speed of light. We can't measure gravitational waves more precisely without confronting quantum uncertainty. We can't detect fainter sources without longer integration times or larger collectors. We can't resolve smaller angular scales without bigger baselines or shorter wavelengths. Every observation bumps against physical limits, but we keep finding ways to push those limits further. Better mirrors, larger arrays, more sensitive detectors, clever analysis techniques that extract signal from noise, and every improvement reveals more. More distant quasars, more gamma ray bursts, more neutron star mergers, more magnetars. The universe keeps providing examples. We keep finding them. The detection rate increases with our sensitivity, which means there's more out there. Fainter objects, more distant events, phenomena we haven't yet characterized. Every survey finds outliers, objects that don't fit the models, too luminous, too compact, too variable. These outliers drive theory forward. Force refinements reveal new physics. GRB 221009A was an outlier, brightest ever detected. It's saturated detectors designed for bright events. We had to use indirect methods to measure its peak flux. Too bright for direct observation. That happens. The universe occasionally produces something so extreme it breaks our instruments. Not because the instruments are poorly designed, they're built for the typical case, the statistical average. But the universe has a tail. Extreme events that occur rarely, but do occur. We design for the expected, then nature surprises us, and we learn. Upgrade the detectors, expand the dynamic range, build backups with different sensitivities. The next generation of instruments will handle brighter bursts, wider fields, higher time resolution. They'll find more events, rarer phenomena, and some of those will be outliers for the new instruments. It's iterative. Each generation of detectors reveals a new population, which informs the next generation, which finds more. The process continues, but there are hard limits. Cosmological limits. We can't see past the cosmic horizon. Light from beyond that distance hasn't reached us yet. As the universe expands, that horizon grows, but it grows at the speed of light, which means distant objects recede faster than their light can reach us. There's a sphere of observability. Everything inside is potentially detectable. Everything outside is forever beyond our reach. That sphere has a finite volume, which means a finite number of objects. We can count them statistically. We can't observe every galaxy, but we can survey representative volumes and extrapolate. Current estimates suggest around 2 trillion galaxies in the observable universe. Each galaxy has a supermassive black hole. Most are dormant. Some are active. A small fraction are quasars. An even smaller fraction are the brightest quasars. The extreme tail of the luminosity distribution, we can calculate the number of magnetars, the supernova rate, the fraction that produce neutron stars, the fraction of neutron stars that are magnetars. Multiply the probabilities, get an estimate. Gamma-ray bursts are rarer, a few per galaxy per million years. Multiply by 2 trillion galaxies. Divide by the observable timescale. Get a rate. Compare to detection rates. The numbers match. That's consistency. The models work. The statistics are correct. We understand the populations. Not every individual object, but the ensemble, the distribution, the average properties, which brings us back to power. The most powerful individual object is probably an outlier, something rare. But rare doesn't mean non-existent. The universe is large. Outliers exist. We just haven't found all of them yet. The brightest quasar we've detected might not be the brightest that exists, just the brightest we've seen. There could be brighter ones beyond our detection limit, or pointed away from us, or obscured by dust. Same for gamma-ray bursts, same for magnetars, same for everything. Our catalogues are incomplete, biased toward bright, nearby unobscured sources. The true maximum might be larger, the true distribution might extend further. We're sampling the observable subset, not the complete population, but we can estimate, extrapolate, use the observed distribution to predict the unobserved tail. Statistical methods, Bayesian inference, maximum likelihood. Those methods suggest the brightest quasars we've found are probably within a factor of a few of the absolute maximum. Same for gamma-ray bursts. The outliers are rare enough that we've likely found representatives near the extreme. Magnetars are harder, smaller sample size, more difficult to detect. The strongest fields we've measured might be average, or we might have found the extreme cases. Uncertainty remains. Black holes scale with galaxy mass. The most massive galaxies host the most massive black holes. We've found black holes with masses of tens of billions of solar masses. Could there be larger ones? Probably. In the most massive galaxy clusters. We just haven't surveyed them all yet. But there's a practical maximum. Galaxy mergers produce larger black holes. But mergers take time. The universe has a finite age. There's a limit to how many mergers can occur, which limits the maximum black hole mass. Current estimates suggest the maximum is around 100 billion solar masses. Maybe higher, but not arbitrarily high. The universe isn't old enough for more. That maximum mass corresponds to a maximum gravitational influence, maximum accretion power, maximum jet luminosity. Not infinite, bounded by cosmology. So even the extremes have limits, physical limits, observational limits, statistical limits. The most powerful object in the universe is powerful, but not infinitely so. It operates within the same physical laws as everything else, just pushed to the edge of what those laws allow. That's the real answer. The universe has extremes, but the extremes are finite, bounded by physics, by time, by space, by probability. Understanding those bounds is understanding the universe itself, which raises an interesting question. If the extremes are bounded by physics, what determines those bounds? Start with energy. The most powerful objects convert mass to energy. Black holes do this through accretion. Matter falls in, heats up, radiates. The efficiency depends on spin. A non-rotating black hole converts about 6% of infalling mass to energy. That's already better than fusion. Stars convert less than 1%, but spinning black holes can reach 42% efficiency. Nearly half the mass becomes radiation. That's the theoretical maximum for accretion. The Ophiuchus supercluster eruption consumed 270 million solar masses over 100 million years. Most of that mass went into the black hole, but some became energy, jets, radiation, shock waves. The cavity it carved is 1.5 million light-years across, 10 times the Milky Way's diameter. That's sustained power, not a brief burst. Continuous output for geological timescales. Compare to gamma-ray bursts. They release more energy in seconds than the sun will produce in its entire lifetime, but they're transient, brief. The total energy might be comparable to what a quasar emits in a year, compressed into moments instead of spread across time. So which is more powerful? The brief intense burst or the sustained output? Depends on your definition. Peak luminosity favors gamma-ray bursts. Total energy output favors quasars and active galactic nuclei. It's like comparing a camera flash to a light bulb. One is brighter for an instant. The other provides more total light over time. Magnetars add another dimension. Their power isn't primarily electromagnetic radiation. It's magnetic field strength. The field itself does work, twists spacetime, affects particle trajectories at cosmic distances. A magnetar's magnetic field can warp atoms into elongated shapes, change the vacuum properties of space itself. That's a different kind of power. The December 2004 starquake from SGR 1806-20 released more energy in a fraction of a second than the sun produces in 100,000 years. But that wasn't continuous output. It was a crack in the crust, a sudden release. The magnetar itself maintains its field constantly. That requires energy. Where does it come from? Rotational energy. Magnetars spin. Not as fast as millisecond pulsars, but fast enough. The rotation powers the magnetic field. As the field does work, the rotation slows. Gradually, over thousands of years, the rotational energy gets converted to magnetic energy, which gets released as X-rays and gamma rays. So the power source is kinetic energy from the original supernova, stored in rotation, released slowly through magnetic processes. It's a cosmic battery, charged by stellar collapse, discharged over millennia. Black holes have a different power source. Gravity, specifically, gravitational potential energy. Matter far from a black hole has high potential energy. As it falls closer, that potential energy converts to kinetic energy, then to heat, then to radiation. The deeper the gravitational well, the more energy available per kilogram of matter. That's why the most massive black holes can be the most luminous. They have the deepest wells. Matter falling in can release more energy, but there's a limit, the Eddington limit. Radiation pressure pushes outward. Gravity pulls inward. When radiation pressure equals gravitational force, accretion stops. No more matter can fall in. The luminosity is capped. For a given black hole mass, there's a maximum luminosity, Eddington luminosity, proportional to mass. A billion solar mass black hole has an Eddington luminosity about 1 billion times the sun's. That's roughly 10 to the 47th power ergs per second, which matches the brightest quasars, but some objects exceed the Eddington limit. Briefly, during special circumstances, super-Eddington accretion happens when matter falls in so fast that radiation can't escape efficiently, gets trapped in the flow, allows more matter to accrete, produces higher luminosities, but it's unstable. can't last long. That might explain ultraluminous quasars, the ones pushing 10 to the 48th power ergs per second. They're temporarily exceeding their Eddington limit, consuming matter faster than steady-state physics allows. It'll end. Eventually, the system will stabilize. But for now, they're extraordinarily bright. Gamma-ray bursts might also involve super-Eddington processes. The jets definitely do. A relativistic jet carries enormous energy, more than the Eddington luminosity of the central engine. But the jet is directional, beamed. So it doesn't push on the surrounding matter the same way isotropic radiation does. Different geometry, different limits. Which brings up blazars. They're quasars with jets pointed at us. We see the jet head-on. That makes them appear brighter. Relativistic beaming. The light is compressed, blue-shifted, concentrated. A blazar might have the same intrinsic power as a regular quasar, but we see it amplified by geometry. Measurements show apparent speeds in blazar jets exceeding 25 times the speed of light. That's not real faster than light motion. It's an illusion. The jet is moving toward us at nearly the speed of light, close to our line of sight. The light emitted at different times arrives at Earth within short intervals. Makes it look like the jet is moving faster than it actually is. The true speed is around 99% of light speed. Still insanely fast. At those velocities, relativistic effects dominate. Time dilation, length contraction, Doppler boosting. The energy we measure is dramatically enhanced compared to what a stationary observer would see. So blazars aren't necessarily more powerful than other quasars. They're just pointed at us. Which raises a question. How many powerful objects are out there that we can't see because they're pointed away from us? For every blazar we detect, there might be hundreds of similar objects with jets aimed elsewhere. We only see the ones aligned with Earth. That means the total population of jet-producing black holes is much larger than the blazar count suggests. Same logic applies to gamma-ray bursts. We see the ones with jets pointed at us, but the jets have narrow opening angles, maybe 5 to 20 degrees. That means for every GRB we detect, there are dozens or hundreds happening with jets pointed in other directions. We miss them entirely. The true rate of these events is higher than the observed rate. Multiply by the geometric correction factor. Account for the beaming. Get the actual rate. That affects our understanding of how common these extreme objects are. They're rare in terms of what we detect, but less rare in terms of what actually occurs. The universe is producing these events constantly. We just don't see most of them, which means the most powerful object in the universe might be something we haven't detected yet. Not because it doesn't exist, but because it's not pointed at us, or it's too far away, or obscured by dust, or in a part of the sky we haven't surveyed. Current surveys cover a fraction of the sky at any given time. Over all time, we've covered more, but not with uniform sensitivity. Deep surveys cover small areas. Wide surveys are shallower. You can't do both simultaneously with limited telescope time. So there are gaps, regions of parameter space we haven't explored, faint distant objects, transient events that occurred when no telescope was looking, highly obscured sources that only show up in infrared or radio wavelengths. We've found some, but not all. Future telescopes will help. The James Webb Space Telescope is already finding distant quasars that were invisible to previous instruments. The Vera Rubin Observatory will survey the entire visible sky every few nights. catching transients, building time-domain astronomy. The Square Kilometre Array will detect radio sources with unprecedented sensitivity. Each new instrument expands the observable universe. Not in distance necessarily, but in the range of phenomena we can detect. Different wavelengths, different timescales, different sensitivities. Each one reveals objects that were always there but invisible to older technology. That means our current answer to most powerful object is provisional. It's the most powerful we've found so far. With current instruments, in the regions we've surveyed, using the techniques we have, the real most powerful object might be hiding just beyond our detection threshold, waiting for the next generation of telescopes, or the one after that. But even with perfect instruments, there's a limit. The observable universe has a finite volume, roughly 4 × 10 to the 80 cubic meters. That volume contains a finite number of galaxies, around 2 trillion. Each galaxy has a finite number of possible extreme objects. Multiply the probabilities, get an upper bound on the total count. Within that finite population, there's a most powerful object, singular. The one that happens to be at the extreme of the distribution. It exists. Somewhere. We just don't know where. Could be in a galaxy cluster we haven't observed. Could be at high redshift. Could have been active billions of years ago and is now quiescent. We're seeing the universe at a particular moment in cosmic time. Objects evolve. What's most powerful today might not have been a billion years ago. What was most powerful then might be dormant now. Time adds another layer of complexity. The universe has a history. 13.8 billion years. Objects form, evolve, merge, die. The extreme population changes over time. In the early universe, the first quasars were forming. Smaller black holes, lower masses, lower luminosities, but there were fewer of them. As the universe aged, black holes merged, grew larger, became more massive, reached higher peak luminosities, but the gas supply decreased. Fewer galaxy mergers per unit time, less fuel for accretion, so the number of active quasars decreased. Today's most luminous quasars might be less luminous than the peak quasars at redshift 2 or 3, several billion years ago, when the universe was younger, more gas-rich, more active. We can observe those distant quasars, see them as they were, but we can't observe the present-day versions. The light hasn't reached us yet. So the most powerful object that exists right now might not be the most powerful object we can currently observe. Light travel time creates a delay. We see the past, not the present, if we could freeze the universe. Take a snapshot at this exact cosmic time. Survey everything simultaneously. We'd find the true current most powerful object, but we can't. We're stuck with the light cone, the past light cone. Everything we see is history. That history is valuable. It tells us how objects evolve, how populations change over time, how the universe transitions from one era to another. But it means most powerful object in the universe is ambiguous. Do we mean most powerful currently existing, or most powerful we've observed, or most powerful that ever existed? Different questions, different answers. The most powerful ever might have been an early supermassive black hole, accreting at super Eddington rates in a dense protogalactic environment, consuming gas at phenomenal rates, producing a quasar brighter than any we see today. It existed for maybe 100 million years, then ran out of fuel, became quiescent, still exists now as a dormant black hole. but we remember its active phase. Or maybe the most powerful ever was a gamma-ray burst from a hypernova, a star hundreds of times the Sun's mass. Possible in the early universe with different metallicity. It collapsed, formed a black hole, launched jets, produced a GRB brighter than any modern one, briefly outshone the entire observable universe at that time, then faded. The black hole remains, but the burst is long over. We don't know. The past is incomplete. The present is unobservable. The future is uncertain. We work with what we have, the observable subset, and make inferences about the rest. But one thing is clear. Whatever the most powerful object is, it's operating at the edge of what physics allows. Maximum efficiency, optimal conditions, extreme parameters. It's not violating physical laws, but it's pushing them to their limits. That's what makes it the most powerful. Not just that it's powerful, but that it's as powerful as anything can possibly be, given the constraints of relativity, thermodynamics, quantum mechanics, gravity, all the fundamental forces. The most powerful object is the one that's found the maximum solution to the optimization problem. And somewhere in the cosmos, it exists. But we can search, we can observe, we can measure, and we can discover the next record holder. Because the universe is still active, still evolving. Somewhere right now, a quasar is brightening, a magnetar is erupting, a gamma-ray burst is launching. The cosmos doesn't stop for our convenience. It continues operating at scales that dwarf human comprehension. Every second, somewhere in the observable universe, matter is being converted to energy at near maximum efficiency. Black holes are feeding, stars are exploding, neutron stars are colliding. The machinery of cosmic power runs constantly, without pause, without rest. And here's what makes it fascinating. We're getting better at finding these objects. Technology advances, telescopes improve, detection methods become more sensitive. The James Webb Space Telescope can see further back in time than ever before, to epochs when the first quasars were forming, when supermassive black holes were just beginning to grow. LIGO and Virgo detect gravitational waves from neutron star mergers, from black hole coalescence, from events that would have been invisible just decades ago. We're expanding our observational capabilities, pushing into new wavelength regimes. Gamma-ray satellites monitor the entire sky, waiting for the next burst, the next explosion, the next cosmic catastrophe. Radio telescope arrays scan for transient events. Optical surveys track changing brightness across millions of objects. We're building a real-time monitoring system for the universe, watching for the most powerful events as they happen. Consider what's been discovered just in recent years. J0529-4351, the fastest growing black hole known, 17 billion solar masses, consuming more than a solar mass per day. Its accretion disk so luminous it outshines 500 trillion suns. That's not a typo. 500 trillion, from a region smaller than our solar system. The efficiency is staggering. Matter falling into the black hole reaches a significant fraction of light speed. Friction in the accretion disk heats it to millions of degrees. It glows across the entire electromagnetic spectrum. X-rays, ultraviolet, visible light, infrared, radio waves. Every photon detector we point at it saturates with signal. And yet this object is 12 billion light-years away. We're seeing it as it was when the universe was young, 1/10 its current age. Imagine what it's doing now, after 12 billion more years of growth. It might have consumed an entire galaxy's worth of gas, or it might have gone quiescent, run out of fuel, become dormant. We won't know for 12 billion years. When the light from its current state finally reaches us. But that's just one object, one data point. The surveys continue. SDSS, Sloan Digital Sky Survey, has catalogued over 900,000 quasars, each one powered by a supermassive black hole, each one converting mass to energy at tremendous rates. The distribution tells us about galaxy evolution, about how structure formed, about when and where the most extreme conditions occurred. Statistical analysis reveals patterns. Peak quasar activity occurred at redshift 2 to 3, about 10 billion years ago, when galaxy merger rates were higher, when gas fractions were larger. The universe was smaller, denser, more violent. Collisions were common. Every collision triggered star formation, fed central black holes, created quasars. The cosmic landscape was ablaze with activity, far more than today. Our current epoch is relatively quiet, sedate. The universe has aged, spread out, cooled down, yet individual events still reach extraordinary power levels. GRB 221009A, detected October 9, 2022. The brightest gamma ray burst ever recorded. It saturated detectors, overwhelmed sensors designed for extreme events. The burst lasted over 300 seconds, 5 minutes of continuous high-energy radiation, from a source 2.4 billion light-years away. Despite that distance, it was visible in amateur telescopes. For a brief moment, a stellar explosion halfway across the observable universe could be seen with backyard equipment. The total energy released approaches incomprehensible numbers, converting multiple solar masses worth of matter into pure radiation. In minutes, the mechanism, a massive star collapsing, forming a black hole, launching relativistic jets. The jets punch through the stellar envelope, break free into space, accelerate material to 99.99% light speed. When that material collides with surrounding gas, it produces the gamma ray emission we detect. The beaming is crucial. The jets are narrow, perhaps a few degrees wide. We only see the burst because one jet is pointed almost directly at us. If it were aimed elsewhere, we'd miss it entirely. Which means for every GRB we detect, hundreds occur in directions we can't observe. The true rate of these events is much higher than detection rates suggest. And then there's the Ophiuchus supercluster eruption. Discovered in 2020 through careful analysis of X-ray data, a cavity in the intracluster medium, a void 1.5 million light-years across, 10 times the Milky Way's diameter, carved out by a supermassive black hole eruption. The central black hole has a mass of 7 billion suns. It consumed 270 million solar masses of material over 100 million years. The outflow created shockwaves, jets, bubbles of hot plasma. The cavity represents displaced matter, gas pushed aside by the force of the eruption. The energy required is staggering, 5.7 million times more than the most powerful gamma-ray burst, but released over a much longer timescale. Sustained power output for millions of centuries. It's the most energetic event ever detected since the Big Bang. A testament to what supermassive black holes can do when properly fed, when conditions align, when accretion rates maximize. These discoveries reshape our understanding. They push the boundaries of what we thought possible. Each new detection forces theoretical revisions. Models must accommodate observations. Simulations must reproduce measurements. The interplay between theory and observation drives progress. We predict, we observe, we refine, we predict again. The cycle continues. Our picture of cosmic power becomes more complete, more accurate, more nuanced. But there's a pattern emerging. The most powerful objects share characteristics. They involve extreme gravity, compact masses, high accretion rates, efficient energy conversion. They operate at the limits of physical law, maximum efficiency, optimal conditions. They're not common, rare events, special circumstances. But when they occur, they dominate. They outshine entire galaxies. They release more energy than billions of stars combined. They reshape their environments, create structures visible across cosmic distances. They're the universe showing what's possible when conditions are just right. Consider the physics involved. Einstein's equations allow for black holes, supermassive ones, stellar mass ones, intermediate mass ones. The math doesn't forbid them, it predicts them. General relativity describes space-time curvature, how mass warps geometry, how extreme curvature creates event horizons, points of no return, the Schwarzschild radius, the boundary where escape velocity equals light speed. Inside, nothing escapes. Outside, everything's possible. The accretion disk forms outside. Matter spirals inward. Friction heats it. Magnetic fields thread through it. Instabilities develop. Jets launch. The system self-organizes into a power generator, converting gravitational potential energy into radiation, into kinetic energy of outflows. The efficiency can reach 32%. Nearly a third of infalling mass becomes energy. Compare that to nuclear fusion. The Sun converts 0.7%, less than 1%. Black hole accretion is 40 times more efficient. That's why quasars outshine galaxies. Why active galactic nuclei dominate their hosts. The conversion mechanism is simply better, more effective, more powerful. And it scales. Small black holes, stellar mass, can produce microquasars, smaller versions of the same phenomenon, but with lower total luminosity. Larger black holes, supermassive, can produce quasars, ultraluminous AGN. The power scales with mass, with accretion rate, with efficiency. The biggest, fastest feeding black holes produce the most power. It's a direct relationship. More mass, more fuel, more output. The universe has tested this across cosmic time, across all mass ranges. The pattern holds. Black hole accretion is the most powerful sustained energy source we know. But what about transient events? Gamma-ray bursts win that category. Brief, intense, concentrated. A hypernova collapse, a neutron star merger. The energy release is explosive, sudden. In seconds, the output exceeds what the Sun produces in 10 billion years. The peak luminosity is unmatched. Nothing shines brighter. For those few seconds, the GRB is the most luminous object in the universe, visible across cosmic distances, detectable from the edge of the observable universe. Then it fades. The afterglow persists, days, weeks, months, but the peak passes. The event ends. The source becomes dormant. A black hole remains, a neutron star, an expanding debris cloud. The power was temporary, spectacular, but brief. So when we ask about the most powerful object, we need to specify timescales. Sustained power, quasars, peak luminosity, gamma-ray bursts, total energy release, the Ophiuchus eruption, magnetic field strength, magnetars. Each category has its champion. Each type of power has its exemplar. The universe contains multiple forms of extremity. different ways to be powerful, different mechanisms, different timescales, different manifestations. They're all real, all measurable, all operating within the same physical laws, but optimizing for different parameters. And we're still discovering, still observing. The next generation of telescopes will reveal more. The extremely large telescope, 30 meters in diameter, ground-based, adaptive optics to correct for atmospheric distortion. It'll see further, resolve finer details, detect fainter objects. The Square Kilometre Array, a radio telescope network spanning continents, unprecedented sensitivity. It'll detect transient radio events, fast radio bursts, pulsar timing, quasar variability. The Laser Interferometer Space Antenna, LISA, a space-based gravitational wave detector, 3 spacecraft flying in formation, millions of kilometers apart. It'll detect supermassive black hole mergers, events invisible to LIGO, too low frequency, too massive. These future instruments will expand our view, show us objects we can't currently detect, events we're missing. The most powerful object might not have been found yet. It might be out there, waiting, beyond our current detection threshold. But based on what we know now, the answer is clear. For sustained luminosity, quasars reign supreme. J0529-4351 currently holds the record. Fastest growing black hole, most luminous persistent source, over 500 trillion solar luminosities. From a region smaller than our solar system, it's the most powerful object we've observed, the current champion. Until something brighter is discovered, until a more luminous quasar is found, the title is provisional, temporary, because the universe is vast. Our surveys are incomplete, and somewhere in the cosmic dark, an even more powerful object might be shining, feeding, growing, converting mass to energy at rates we've never measured. We just haven't found it yet. But we're looking, and we'll keep looking, because that's what we do. We search for extremes, we measure the universe, we find the boundaries of what's possible, and when we discover the next record holder, we'll know we're one step closer to understanding the full range of cosmic power, the complete spectrum of what reality allows, from the smallest particles to the largest structures, from quantum fluctuations to supermassive black holes, from the gentlest whisper to the loudest roar. The universe contains it all, and the most powerful object is simply the one that's found the maximum, the peak, the upper limit, the answer to how powerful can anything possibly be. And now you know what that is. The universe operates at scales that make our most extreme achievements look quaint. Every nuclear weapon ever detonated combined wouldn't equal 1 second of a magnetar's starquake. Every power plant on Earth running for a century wouldn't match the output of a quasar for a microsecond. We've built machines that can split atoms, but the cosmos splits space-time itself. And here's what's remarkable about that. We understand it, not just in vague terms. We can calculate the energies, we can measure the distances, we can predict the behavior. The equations describing a quasar's accretion disk are the same ones describing water swirling down a drain, just applied to regimes where gravity is strong enough to warp space, where velocities approach light speed, where temperatures reach millions of degrees. The physics doesn't change, it scales. Maxwell's equations describe both the magnetic field in your refrigerator magnet and the quadrillion Gauss field of a magnetar. Einstein's field equations govern both GPS satellites and black hole event horizons. The Navier-Stokes equations apply to both coffee stirring in your cup and plasma flowing in an accretion disk. Same math, different parameters. That's the power of physical law. It's universal, consistent, scalable, but understanding something doesn't diminish its magnificence. Knowing how a magnetar generates its field doesn't reduce the fact that it could kill you from 1,000 kilometers away by destroying your atomic structure. Calculating a quasar's luminosity doesn't change that it outshines hundreds of billions of stars. Measuring a gamma-ray burst doesn't make it less impressive that it releases 10 billion years of solar output in seconds. The numbers stand alone. They need no embellishment. 500 trillion solar luminosities, quadrillion Gauss magnetic fields, energy outputs that dwarf the combined starlight of the observable universe. These aren't metaphors, they're measurements, actual values determined from actual observations. The universe genuinely produces phenomena at these scales. And we're part of it, not separate observers, but participants. The carbon in your DNA was forged in stellar cores. The oxygen you breathed came from supernova explosions. The calcium in your bones was scattered by dying stars. You're constructed from the products of cosmic violence, made of stardust. Literally, not poetically. Literally. That means when you observe a quasar, you're using atoms that once participated in similar processes. When you measure a gamma-ray burst, you're employing elements created in comparable explosions. The subject and the observer are made of the same stuff, governed by the same laws, part of the same cosmic story, which makes the question of the most powerful object more than academic curiosity. It's about understanding the processes that created you, that shaped the matter comprising your body, that built the planet you stand on. The forces we're describing aren't distant abstractions. They're the mechanisms that constructed reality itself. So what's the answer? What's the most powerful object in the universe? Depends on your metric. Sustained electromagnetic luminosity points to J0529-4351, a quasar consuming more than a solar mass per day, radiating at 500 trillion solar luminosities, visible across 12 billion light-years of expanding space. That's the current record holder for persistent brightness. Peak electromagnetic output points to gamma-ray bursts, GRB 221009A, released energy approaching the sun's total rest mass. In minutes, briefly outshone everything else in the universe at gamma-ray wavelengths. That's the champion for explosive events. Magnetic field strength points to magnetars, fields exceeding 10 to the 15th Gauss, a quadrillion times Earth's field, strong enough to warp atoms, to alter vacuum properties, to make space-time itself behave differently. Gravitational wave luminosity points to merging supermassive black holes. 200 million solar mass objects spiraling together. In the final second, they emit more power in gravitational waves than all observable stars produce in light. Combined, that's the peak for space-time distortion. Total energy release points to the Ophiuchus eruption, 5.7 million times more energetic than the most powerful gamma-ray burst, released over 100 million years, creating structures visible across cosmological distances. That's the marathon champion. Each category has its winner. Each form of power has its peak. The universe doesn't provide a single answer because power comes in multiple forms, different mechanisms, different timescales, different manifestations. They're all real, all extreme, all operating at the boundaries of physical law. But if forced to choose one answer, For sustained power output measurable by human instruments, the title goes to J0529-4351, the fastest growing black hole known. The most luminous persistent object detected, it represents the maximum steady-state power we've observed, a supermassive black hole feeding at near maximum efficiency, converting mass to energy at rates approaching theoretical limits, sustaining that output for millions of years, shaping its entire galactic environment. That's the most powerful object in the universe, until we find something brighter, something more energetic, something that pushes even further against the limits of what physics allows. The surveys continue, the telescopes improve, the detection methods advance, and somewhere in the cosmic dark, an even more extreme object might be waiting, just beyond our current capabilities, ready to redefine what we mean by powerful, because that's how science works. We find the current maximum, we study it, we understand it, then we push further, look deeper, search harder, and eventually we find something more extreme. The process never ends. There's always another limit to test, another boundary to probe, another question to ask. The universe keeps providing answers. We keep asking questions. And in that dialogue between observation and theory, between measurement and prediction, we gradually map the full range of cosmic phenomena, from the gentlest whisper to the loudest roar, from quantum fluctuations to supermassive black holes, from the birth of atoms to the death of stars. It's all connected, all part of the same magnificent story. And the most powerful objects are simply the ones that found the maximum solution, the peak of what's possible, the upper limit of reality itself.